And welcome back. Yes, my workbench is a little bit sparse today because all we've got is this Arduino on it, because we're not actually going to connect anything to it, but instead what we're going to do is talk about the code that we upload to the chip and how we might optimize that. Now, before we talk about optimizations as though there's some sort of nirvana, some silver bullet to your slow running programs, no, that's not it at all. If you need things to run faster, use a faster processor. But sometimes we can just tweak what the compiler does and make things run the way we expect them to run, especially when we're communicating between different modules, if the Arduino is communicating with something else, for example. What do I mean by this? Well, let's have a look at a very simple example. What do you make of this bit of code? Now, just a quick shout out for PCBWay, especially for beginners who perhaps have never done this before. It really is simple once you get your head around it. Create your PCB design in your favorite CAD program, KiCad or something like that, and then get your Gerber files ready and upload them when you click on this button here. Now, the dimensions are not important. Just put 100 by 100 here. Put how many you want here. Remember, it's $5 for 10 pieces. So put in 10 and then click the quote now button. But I want to talk to you about something else this week. And that's about, are you really going to solder SMT components? Because they will do it for you for a very reasonable sum of $30. But that includes your shipping. So you sort of get it back, don't you? Let's have a look what that means. Now, this is the page you end up on when you specify how you want your board to be assembled, okay? And behind my head, you can see that sign there. Look, free shipping with this PC assembly. So bear that in mind. Now, here you say, how am I going to source the components? The best way is to let PCBWay source them for you. You just give them a list of the components you want in a standard, spreadsheet format. So you say, I want these capacitors of this value and this size. So, for example, you might say, I want a 100 nanofarad capacitor, 0603, and that's capacitor 1. And then capacitor 2 is something else, and so on. You just give them the entire list. They'll go away and find them. And believe me, components are cheap in China, so you'll be pleasantly surprised at the cost. Now, having done all that, you specify down here whether you want through-hole components, which side of the board you want soldered, either top, bottom, or both, and they'll just do the whole thing and send it back to you. It really is a nice way of getting a prototype to you back very quickly without having to get the soldering iron out. So, what are you waiting for? Have a go at PCBWay and try them out now. So, this is no trick questions, by the way. This is a DigitalWrite. We'll assume that the pin mode on that pin is already output, set to output, okay? So we're going to say set it high, set it low, set it high, set it low, as fast as that will allow us to do it. So we should get 2 pulses on that pin. Now, that pin 13 is, yes, connected to the LED on your board, but this is so fast you'd never, ever see anything flash. So we'd have to look at the oscilloscope. So what would you expect to see? That's right, yes, 2 pulses. Let's have a look at what actually is on my oscilloscope now. And there we are, 2 pulses. Brilliant. That's exactly what we'd expect. As the pin goes high and then comes low, high, low. Fine. What would you expect, though, if, for example, we repeated these 2 pulses here? We said, well, actually, I've got this bit of code here. I'm going to put it into a function. Okay, so we call it void flash LED twice and call it a number of times because we want to flash the LED or send out 2 pulses on that pin at least more than once. So we're going to conform to the dry principle. Don't repeat yourself, even though, yes, all right, I know I've repeated the 1 pulse again here, but this is for demo purposes, remember. All right, if we were to replicate this code into a function and then say call that function, what would you get? Yes, you get exactly what you see on that oscilloscope screen now. So 2 pulses, 1, 2, the end. Great. But what happens if we said call that function and then immediately call that function again? Right, 4 pulses. Yeah, because we're calling it twice, aren't we? No, you wouldn't actually. Why? Well, if I scroll my oscilloscope here to the right so you can see a little bit more of what happens. Oh, look. So we have 2 pulses. Yep, that's what I'd expect. But then we've got this massive long delay here. I say massive long. It's, a few microseconds long. And then we have the other 2 pulses. Why have we got a gap between the 2 pulses when we've said run that little function to put this pulse on pin 13 twice, and then immediately do it again. Well, the problem there is we said immediately. Well, things don't happen immediately in the computer world because we've now written it as a function. Let's have a look at the code and you'll be able to follow what I mean. Right, so the code that flashes that LED so quickly you can't see it, but actually does output something on the pins that we can see on that oscilloscope as right now, it's this code here. Now, let's not worry about this too much. I'll explain that in just a second. It's the equivalent, though, of saying 13 high, 13 low, and then do it again. So, yes, we do get our 2 pulses as shown on the oscilloscope, right? Nothing fancy about that. Except, if I was to show this, or try to demo it, using DigitalWrite, DigitalWrite is so slow in comparison to what I've done here, that you'd never actually see the difference. In fact, what you'd see is the first pulse, yeah, that would be, well, it would be later than what it is there because it's so slow. So the first pulse might be where the second pulse is, and the second pulse would be somewhere over here. And if we were to call this routine twice, so you expect 4 pulses, even though we saw earlier that there's this massive gap, those 4 pulses using DigitalWrite would be spaced nice and equally apart, and it would look like it's working, except that it would be awfully slow. Now, normally, it doesn't matter if it's slow. I mean, if you're turning a relay on, or turning on an LED or something, who cares? Yeah, a few microseconds amongst friends, I mean, come on. But if you are in a critical situation where you're talking to other microcontrollers or perhaps sensors or something, and it has to be spot on, then that's not fast enough. So we revert to the standard underlying method of controlling those pins directly. Now you might go, well, if we can do it a different way and control them directly, why has Arduino written this thing called DigitalWrite? And the reason they've done that is because they're taking a belt and braces approach. One, it looks easy to write, doesn't it? DigitalWrite, pin number, high or low. It's all very understandable. And behind the scenes, they're doing some clever checking to say you're trying to set it high, but is the pin actually in output mode or not? And can I do this, that, and the other? And there's a few little checks it does. And that works 99.999% of the time, except when you want really fast pin access or simultaneous pin changes. For example, if we wanted to change pin 13, 12, 11 and 10 all at the same time using DigitalWrite, you could do it DigitalWrite 11, 12, 13, whatever, but it wouldn't be at the same time, would it? There would have to be a tiny delay between each of those pins going high. But using what I've got here, which is port B, this is direct register manipulation now for the port, which is a collection of pins, you can set any number of these pins high at the same time, and I do mean at the same time. The hardware will switch them instantly. I don't want to get too deep into here, just accept that at the moment pins 8 to 13 are controlled by port B, and DigitalWrite will be doing things behind the scenes rather like this. But I just want to skim over this and say, all right, the first 2 bits on here are not used because pins 14 and 15 in this 8-bit byte, they're analog pins or are not controlled by port B. Okay, so we skip the first 2, that they will do nothing. So pin 13 is that first one, then 12, 11, 10, 9, 8. Fine. It's much quicker to do it like this, but much harder to see what's going on, which is why Arduino say, do you really need to do this? Are you sure you'd want to write this stuff down here rather than this easy to read stuff here? So you have to think, normally you'd write this DigitalWrite stuff. Yeah, I mean, it's easy to understand, but when you need fast, and I do mean fast access to the ports and therefore the pins, this is the way to do it. Let's just assume now that this function here just works. Okay, you can see on the screen that it's outputting 2 pulses and then another 2. Why 2 gap 2? Well, let's look a bit further up in the code. Right, here's my loop, the standard loop from the Arduino. Here's another loop within it to say, do all this twice. We'll come on to that if there's time. But what we're saying is, call this routine down here a number of times. In fact, 6 times I've got it here. Right? So it says, 2 pulses please, and then another 2 pulses, then another 2 pulses. Now you might be asking, well hang on, I can only see 4 on screen. Well, it's so slow that the other pulses have disappeared before the oscilloscope capture them. All right, the oscilloscope can only capture what's on available at any particular time. So it's captured the first 2, but the other 2 are so slow they've sort of dropped off the end. We'll come on to this. And the reason why there's this big long gap between the first 2 pulses here and the second 2 is precisely from what you're seeing here. This call is a call to another function, isn't it? So what happens is when the compiler sees that, it says, oh, you're trying to call another bit of code. Great. Well, whatever I'm doing in my current bit of code, which is the loop function, it says, right, I'll store everything that I've got, all my register values and variables and stuff like that that it needs to store. It says, I'll put those on the stack, right, in a frame, but let's not go into that. It's just going to store them. It will then leap to your other bit of code, in this case, flash LED twice, run all that, and when that function ends, automatically jump back to where it was and go, right, I've now got to restore the stuff that I had on the stack, right, put it all in the right registers. Great, I'm ready to continue. Except that now we're saying, now do it again. It goes, all right, I'll put everything back on the stack then, go and run that bit of code, come back. I think you get the picture. Okay, there's an overhead. And the overhead of putting stuff on the stack and storing stuff, then coming back and restoring it, normally absolutely not an issue. It only takes, you know, a few microseconds. But as we can see here, it's noticeable. Certainly noticeable by other bits of equipment. And it goes, hang on, you're telling me 2 pulses and a big long gap and then another 2. So instead of actually sending out 12 pulses, we've sent out 6 lots of 2 pulses, haven't we? That's not what we want to do here. How do we overcome this? Well, you can tell the compiler, how are you set up at the moment? And of course, Arduino have said, when the GCC compiler puts all your code together, it's trying to optimize for space, because it knows that on the Arduino, you've only got 32K. I say only, I mean, it's not bad, but it knows that people are going to push it to the limits, okay? Incidentally, just as an aside, if you do get stuck about the Arduino and the 32K limit, go and buy one of those new Arduino Mega compact versions. I've shown it ages ago in one of my videos, and then I saw it again on Banggood. I think it was Banggood or AliExpress. I think it was probably Banggood actually. They're only $10, and you have umpteen amounts of space on that. In fact, so big I can't remember what it is. And of course you get 3 UARTs and a couple of I2C buses and things, but all the code runs exactly as it does on the Uno, and at about the same speed as well. The Mega is not a fast machine. It's pretty much the same as an Arduino Uno, but it's got so much more space. But anyway, that was just an aside. So Arduino have told this environment, when you compile this code for all my Arduinites, optimize for space. In other words, keep the thing smaller at the expense of speed. And so that's exactly what the compiler does. It notices that you've got functions down here and you're calling it, and it goes, well, I'm just going to call it and put stuff on the stack and come back and all that, as we've already discussed. But you can say, no, I want you to take this code that is in flash LED twice and put it here where I've called this routine as though I'd written it in there myself, and again and again and again, 6 times in total. Now of course, as a coder or maker, you would never write the same bit of code in there 6 times. It just look stupid, and you know that it's the wrong thing. It doesn't adhere to what's known as the dry principle, which is don't repeat yourself. Write one bit of code and then call it many times. But you can tell the compiler, ignore all that. I've written it separately. We know it's a separate little routine here. So drag all that code back up here and put it in line. That's the key phrase. Now you're probably noticing when I hover over here like that, you get all this stuff coming up now. Look, I mean, it's quite, yeah, I'll come on to that in a minute. But this is the Arduino IDE. So what's the magic phrase or setting that you have to do then to tell the compiler, don't go and jump away and run things in routines, go and bring them back in line? Right, let's have a look at the top of the code for this. Right, here's the code that I've actually commented out at the moment. You can see this line here where it says inline void flash LED twice, because that's what the function's called, isn't it? It's a void, doesn't return anything, flash LED twice. And I'd like it inline, please, compiler. Except if you just put that bit in that I've highlighted, just that, it's more a hint than anything else to the compiler, and the compiler, quite frankly, will just utterly ignore it. Because you're saying, look, could you possibly, you know, inline this little bit of code for me? And the compiler goes, hang on, no, you've requested me to optimize for space, and that most definitely does not optimize for space. So on your bike, I'm doing it my way. Right, okay, compiler wins. But then you can say, as you see here, I want to put an attribute onto this particular function and say always inline. So it's not a hint anymore. It now turns into a command to the compiler. So even though the overall sketch is being compiled to optimize for space, you're saying for this particular function, I'd like it inlined always. No if, buts or maybes, you will put this inline. So let's uncomment that then. There we are. Inline, void flash LED twice, brackets, underscore underscore, that's two underscores there. If you watch the cursor, there's one, and then there's another. Attribute, underscore underscore, two brackets, not just one, two brackets. And then that other bit says always inline if I switch off the oscilloscope. There we are. Okay, so what we've told the compiler now is when you compile this program again now, you will copy all the code in that function as though I'd written it longhand wherever you see it. So there's no more jumps to that function, it's always inline. Okay, let's compile that and upload it and see what happens on the oscilloscope. Right, off it goes, trundle trundle. And before we have a look at the output, I just want to show you in the compile, if we look at the beginning of this compile, this is the bit we're interested in. Now you can see here it says -o, that's the capital letter O, followed by a lowercase s, and that is the optimization level set to space. So optimize the size of this code at the expense of speed, one presumes. Okay, so that's what Arduino have built in to the framework that governs your Arduino IDE, with very good reason, obviously, right? And in some ways it's sort of the safest setting as well, which we'll come on to a discussion about this in a minute. Right, now according to this, I think it said that we've done it, haven't we? It's uploaded. It says, okay, down the bottom here now, it says upload complete. Fine, so it's done it. So if we look at the oscilloscope, I'm going to refresh the oscilloscope, make it, I'll force it to re-trigger, and we'll see what we get. Oh, look, look. Let me just bring them to the left a little bit. Look at this, you get lots and lots of pulses all in one go, look. In fact, we should have 12. If you count them, there should be 12 there. Right, take my word for it, you've got the whole lot. Now, if you remember in the code, let me get to the code bit that we were looking at. So we've got 12 pulses for this 6 calls to flash LED twice, but I've said do it twice. So, in fact, you want 12 and then another 12. But, as you can see from the oscilloscope, the pulses sort of run out at that point, and there'll be a big gap. And the oscilloscope, therefore, didn't capture them because it takes too long. Why is that? Well, look at the code here. We're in a for loop. So the for loop starts off saying, okay, I'll do it once, runs them all through, hits the end of the for loop, and then the overhead, once again, of doing that for loop, going, right, I've got to increment the counter. Is the counter bigger than the maximum that it can be? No, it isn't. I'll go in again. That's enough to slow this down. So we can get our 12 out by having all this in line, but we haven't optimized the for loop to say, I want this quicker, please. Now we can do that as well, Whether we can see it on the oscilloscope is another matter. The attribute you need, which you can see here, in fact, that's commented out, is attribute optimize unroll loops. Yes, and it's literally as crazy as you think it is. Not only have we now copied the code in to this for loop, individual code by the compiler, we can say also, if you can work out how many times I'm going to go around this loop, spread it out. Make all the code just one big long bit of code without any looping in it whatsoever. Yeah, I know, it's crazy, isn't it? But, of course, you can imagine, there's no overhead for the for counter to be incremented and checked and all the rest of it before it comes back into the loop here and does this a second time. So it is very efficient. So if we actually wanted 2 lots to run quickly, so 12 pulses followed again by another 12 pulses without any gap in between, we'd simply uncomment this here, that line, and say unroll those loops. Now I'm not going to do that because the compiler, the oscilloscope rather, is only going to capture so much, and I like it to stop so it doesn't keep refreshing because it muddies the picture. That's the way to do it. All right, now you can experiment with this. Be careful though, because if you just had a small amount of code that would not benefit from unrolling, sometimes the compiler says, I know best. And that is, you're always up against that, to say the compiler, because of all the dozens of other bits and pieces it's got to take care of, might say no. However, by doing this optimize unroll loops just ahead of that particular function, which is our main loop, it will actually work. Now, as you can see immediately ahead of it, there's some other stuff here. So maybe we need to talk about that so you can go away and experiment. Now, when I learned about all this, I was overwhelmed by the hundreds, literally hundreds of individual optimizations you can do. And you'll find the link to the official GCC optimization website down below, and it'll blow your mind. What I would say is, don't fiddle and play about, because you won't know what it is you're doing. All right, but at the front of this sketch, I've got a few notes that might help you. Now, I said that the standard optimization from the Arduino environment itself is this one here, -O, capital O, S, size optimization. That's what's hard-coded into the infrastructure of the Arduino IDE. And yes, you could go away and edit that and turn it into something else, but you'll probably cause all sorts of problems, so I wouldn't advise it. However, it's useful to know the other optimization values that you can have, starting with -O0, which means no optimizations, which you probably don't want because it wouldn't optimize anything at all. -O3, that optimizes everything it possibly can, but can cause some unintended side effects. If you've got some kind of loop inside your program that doesn't seem to do anything, even if it updates a variable, it goes, well, you're not actually using that variable after that, then compiler could snatch it away and go, well, that does nothing, I'm removing it, even though you've put it there to introduce some kind of delay or something, some fixed delay. You know, you want a 10 microsecond delay, and you know that will be 10 microseconds, the compiler could snatch it away. And there's other things about O3, it's all a bit hairy. Unless you really know what you're doing, be careful. Now, O-fast, that will unroll the loops, as we've said. So if you've got a loop and the compiler can work out at compile time how many times you're going to go into that loop, it will just expand it. So there's not a loop anymore. It's just the same bit of code, however many times that your loop was for. In this case here, we had that loop for 2 times, didn't we? It will take that bit of code and multiply it twice. So it all runs monolithically. So your program size is obviously increasing quite a bit now, because we'd have 12 instances of that flash LED function, all hard coded, when in fact it only takes like 2 lines of code normally, but we expand that out. So inefficient in terms of size, but very efficient in terms of speed. So when you need it, you need it. Okay, so OS we've already talked about. O2, that's sort of a balanced optimization. How good or bad it is, well, I'll leave it to you to play about if you're that interested. Now, how do you put these in? Well, I've got this line here, look, just to show you. If we were to uncomment that, that's what it looks like. So you say hash pragma GCC optimize, and then in brackets the string that you're trying to add. You can only add one string, and the last string wins out. So if you put 4 of these lines in somewhere, one of them you say O fast, the other one you say O2, then O0, it says, well, I'm just going to take the last one. But the nice thing about it is you can say, just for this function, I want you to change your optimization value. So everything else can be size optimized, make it nice and small. But for this one particular function, I want you to make it fast, which will unroll your loops, for example. And the way you do that is this bit here. So just before the function you want to optimize, you say hash pragma GCC push options, push underscore options. That means your current optimization values will push them up onto the stack. Then it will look at what you've next put in. So you've got things like this, and it will run that one particular function till it comes down to here. And then you say hash pragma GCC pop options, which means pop them off the stack and re-establish what was previously my options, which in this case is space or size optimizations. So if you have one particular function that really does need to be optimized, but nothing else does need to be that, then you can use this particular push and pop, and it works very well. Whew, there's a lot going on here, isn't there? Now, what I'd say is don't willy-nilly change stuff. If you don't need to, don't, because you'll never see the difference. Unless you've got an oscilloscope and you're looking for particular improvements in a bit of code, you'll never see the difference. But let's take a few concrete examples. So, for example, like on the AT-Tiny85. The AT-Tiny85 chip does not have SPI, and it does not have I2C. And yet I did a video some time ago showing that they both work quite happily. Why? Because the signals being output on the pins were bit bashed out, which means the software is pulsing those pins at exactly the right frequency and time, just like we're doing today here with this pin 13, to emulate SPI and I2C, which normally would be done by hardware. But if you haven't got the hardware option, well, there's no option, is there, other than do it bit bashing using software, and it works very well. Now, of course, if the rest of your code happens to go absolutely bananas and suck the power out of your CPU somehow, sorry, microcontroller, it might be a little bit flaky. But just for general purpose stuff, as I showed in that video, oh, there it is, that one. Yeah, nice video that. Where I'm writing stuff to a screen and doing something else on SPI, it works very nicely indeed. And that is bit bashing exactly the same way as we're doing it here. Obviously, you can't use DigitalWrite when you're bit bashing. It's just far too slow. You have to use the method that I showed you using the port D or B or C, whichever port it is you're going to be using. Okay, there's more information at the top here. There's the official website, this one here. I'll put all these links down in the video below. If you want to talk about other stuff, what I've been doing when I haven't been doing videos for the last month, stay tuned. If you're not interested or haven't even been aware I've been away, then great, see you in the next video. You can skip right to the end and see you in the next video. Oh, you're still here. Okay, first of all then, thank you everybody who's responded to my Benny video. I was greatly touched by all the comments, and it was interesting to note how many of you have gone through a similar thing. Now, there's no way I'm going to forget Benny, but he won't be with us in the videos anymore, unfortunately. So thank you very much for all your comments. They were greatly appreciated. And I'm sorry I couldn't respond to each one individually. It would just taken forever. And frankly, I wasn't in a mindset to do it. Now, the other thing that happened was I was hoping to move house. For anybody who's ever moved house, you will know that it never runs smoothly, does it? So the long and short is, we're not now. Well, not until somebody buys my house again, which may happen, may not. Well, I suppose eventually it will, but you know, not at the moment. There's no serious purchaser. So I'm back doing videos. when somebody does eventually buy my house and eventually I move house, which could be any time in the next 12 months, obviously I'll have to do something about the videos elsewhere because I won't be at my lovely workshop. Oh, that would be a shame, wouldn't it? Anyway, at the moment I'm back online, and it will stay this way until something serious happens regarding house moves. Cool. Okay, I think we're done now. We've mentioned the two things I wanted to mention. So thanks very much for comments. I do enjoy them. Please put your comments down below, and we'll meet up in the very next video. Thanks for watching. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.